Today we're diving into something pretty profound. It's this incredible shift where the universe's most abstract language, mathematics, is no longer just for describing reality. We're now using it to literally build our physical world.
I mean, just let that sink in for a second. This one sentence sums up a whole revolution. It's telling us that the line between a formula on a blackboard and an actual tangible object is getting blurry. Heck, it's starting to disappear altogether.
All right, so let's get into what this really means. For a long time, AI has been this amazing tool for looking at the world we have and making sense of it. But what we're seeing now is a totally new scientific revolution where AI is stepping up as a creative partner. It's helping us discover and even build the world as it could be.
And this slide just lays it out perfectly. Over on the left, that's the AI we're used to. It's fantastic at sorting through data we already have. But look at the right. This is the new game. AI isn't just an analyst anymore, it's an active creator. It's coming up with new hypotheses, dreaming up materials that have never existed on Earth, and just turbocharging the whole process of discovery.
So, to make this less abstract, let's zoom in on one of the most mind-bending frontiers, using AI to literally design and create new kinds of matter. Yeah, we're talking about forging materials atom by atom right from a mathematical blueprint.
Say hello to MatterGen. This is a perfect example of what we're talking about. It's a project from Microsoft's AI for Science team, and it doesn't just predict how known materials will behave. No, it generates the atomic blueprints for completely new ones. This isn't just theoretical. It means we can design materials for a specific job, like, say, a super-efficient battery or a next-generation superconductor.
So how in the world does it work? Well, the process is just fascinating. It literally starts with nothing but digital chaos, a random cloud of atoms. Then, kind of like how an image AI creates a picture from TV static, MatterGen starts cleaning up the noise. But it's not just guessing. It's being guided by the fundamental laws of physics and the specific properties we told it we want. And slowly, step by step, out of that chaos, a perfect, stable, and totally new crystal structure just emerges.
Okay, so this brings up a huge question. It's one thing to design a flawless crystal inside a computer, but it's a completely different challenge to actually build it, to measure it, and to have our machines interact with it in the real world. How do you bridge that gap between digital perfection and messy physical reality?
The answer, it turns out, is in a field called metrology, which is the science of measurement. It's really the unsung hero in all of this. It's the discipline that makes sure our physical world can be described, built, and controlled with absolute mathematical precision.
You see, for any of this to work, you need an unbroken chain of trust. Every measurement a machine makes has to be traceable all the way back to a single, ultimate standard, a process overseen by places like the National Institute of Standards and Technology, or NIST. This painstaking calibration is the absolute bedrock of precision. Without it, the robots building your car or the sensors in a science lab are basically just winging it.
Let's look at a really cool, practical example. Think about a self-driving car or a robot that uses a fisheye lens to get a super wide view of the world. The problem is, that view is incredibly warped. So how do you teach a machine to see a straight line when its own eye is fundamentally curved?
The solution is brilliantly elegant. It's something called a geometric jig. What you're seeing here is a HelioPix grid, a mapping tool that was actually borrowed from astrophysics for mapping the night sky. We use it here as a physical calibration tool. By showing this mathematically perfect grid to the distorted camera, we can teach it how to map every single warped pixel back to its true position on a perfect sphere. We are literally using an abstract geometric pattern to give a machine perfect vision. How cool is that?
So we've seen how geometry can forge physical materials and give our machines physical precision. Now, let's switch gears and see how these exact same principles are being used to build something equally critical: digital trust.
One of the biggest roadblocks for AI right now is the black box problem. We can have an AI model that's incredibly accurate, but if we can't figure out how it's making its decisions, can we really trust it? Especially when the stakes are high, like in medicine. This is why there's such a huge push for what's called explainable AI, or XAI.
So where does geometry fit in? Well, a big part of the answer is in post-quantum cryptography. This is the race to build encryption that can stand up to future quantum computers. And a core idea here is called learning with errors, or LWE. The basic idea is that you hide a secret inside a mathematical system that's intentionally filled with a bunch of random noise, which makes the real secret incredibly hard to find. Now, the reason LWE is so tough to crack all comes down to its geometry. The problem is basically like trying to find a single specific point inside a massive high-dimensional lattice. And the best way to picture these lattices, think of them as perfectly structured, infinitely complex digital crystals.
It's the geometric structure of this digital crystal that gives it its strength. Placing a secret message at a specific point inside of it is easy if you know how. But for an outsider trying to find that one point without the key, it's like trying to find one particular grain of sand on an entire planet. The geometric complexity alone makes it almost impossible.
And that brings us right back to trust. When we build our security and our AI on top of these provably hard geometric problems, we're building on a foundation of mathematical truth. The system is secure not because we think it is, but because the math proves it is. This is how we get to AI systems that aren't just smart, but are also transparent and verifiable.
So we've gone on quite a journey, right? From AI creating physical matter, to using geometric jigs to calibrate machines, all the way to securing our digital lives with digital crystals. Let's zoom out one last time, because there's a beautiful, deep connection tying all of this together.
This quote is just wow. It's connecting the dots between a practical 3D printed object, that piece of resin, and some of the most esoteric, complex concepts in all of pure math, like the monster group and Niemeyer lattices. These are ideas that describe symmetries at a level that's hard to even imagine. The quote is suggesting that the same deep geometric truths are echoing everywhere, from the materials we make to the most abstract reaches of human thought.
And that's where we'll end it. Not with a neat little summary, but with this idea. What's happening right now isn't just about better computers or cooler materials. It feels like we're starting to tune into the underlying music of reality itself. A kind of final symphony, where atoms are the notes, algorithms are the instruments, and the entire score is written in the pure, elegant language of geometry.